This video is the second of two videos on integers in Mathematics 7. In this video, we'll focus on multiplying and dividing, as well as order of operations. The first video addressed representing, adding, and subtracting integers. We encourage you to watch that first video before this one. Integers can be used when calculating golf scores or changes in temperature. We'll return to both of these contexts later. Let's begin by exploring multiplication, starting with whole numbers. Take a moment to think about this partial times table. The first number, or factor, appears horizontally. The second, vertically. What patterns can you find? There are many patterns that you might have found. For example, you might have spotted a pattern in this column. Starting at the top, positive 5 times positive 5 is positive 25. Moving down, positive 5 times positive 4 is positive 20. Notice that the product has decreased by 5. This is repeated for positive 5 times positive 3, positive 2, and positive 1. This pattern extends to positive 5 times 0. What comes next? Continuing to subtract 1 from the second factor and 5 from the product shows that positive 5 times negative 1 must be equal to negative 5. Extending similar patterns in the other columns fills in the rest of this row. This can be repeated from positive 5 times negative 2 to positive 5 times negative 5. What happens when we expand this table to the left? Again, we'll focus on one of several patterns, that in the top row. Starting at the right, positive 5 times positive 5 is positive 25. Once more, notice that the product decreases by 5 each time. This time, the first factor decreases by 1, while the second factor holds constant. This pattern extends to 0 times positive 5. Can you predict what comes next? Continuing to subtract 1 from the first factor and 5 from the product shows that negative 1 times positive 5 must be equal to negative 5. Moving right to left fills in the rest of this column. And continuing these patterns fills in more of this expanded times table. Notice that the product of negative 1 and positive 5 is equal to the product of positive 5 and negative 1. The commutative property of multiplication extends to integers. This means that the order of the factors does not change the product. The numbers can commute, or move around, without changing the result. Can you fill in the rest of the table? Whether we extend patterns vertically or horizontally, the result is the same. Pay attention to the signs of the factors and products in each of these four quadrants. They can be summarized as follows. Patterns can convince us that these results are true. However, they don't answer why. The next exploration will answer that important question. How many do you see? How do you see them? You might have seen 8 and 8 and 4, or a pair of tens, or 5 groups of 4. This can be expressed as 5 times 4. 4 times 5 is also 20, but we'll save this expression for describing 4 groups of 5. In the first video, we represented integers using two-color counters and number lines. A couple of quick reminders from the first video. One yellow counter represents positive 1, and one red counter represents negative 1. Joining a positive yellow counter with a negative red counter makes a zero pair. We'll use these tools to make sense of what we discovered earlier through patterns, starting with multiplying two positive integers. In positive 3 times positive 5, we can think of positive 3 as adding or depositing 3 groups. We can think of positive 5 as having 5 yellow counters in each group. So, positive 3 times positive 5 tells us to put 3 groups of 5 yellow counters into the rectangle or bank. The 15 yellow counters in the rectangle represent positive 15, confirming that the product of two positive integers is positive. Similarly, positive 3 times negative 5 tells us to put 3 groups of 5 red tiles into the rectangle. The 15 red counters in the rectangle represent negative 15, illustrating that the product of a positive and a negative integer is negative. What about negative 3 times positive 5? We can think of negative 3 as subtracting or withdrawing 3 groups. Positive 5 tells us what's in each group, 5 yellow counters. This presents a challenge. There are no yellow counters to take out. How do we take out what isn't there? Recall that adding one yellow counter and one red counter, together a zero pair, does not change the value of what's inside the bank. This process can be repeated until there are enough yellow counters to remove. Removing 3 groups of 5 yellow counters leaves 15 red counters, or negative 15. This shows that the product of a negative integer and a positive integer is negative. The last permutation is the product of two negative integers. Negative 3 times negative 5 can be modeled by removing 3 groups of 5 red tiles. Once more, we'll have to change what 0 looks like by adding enough 0 pairs. Taking out 3 groups of 5 red counters leaves 15 yellow counters, or positive 15. Next up, exploring division. Suppose you have 12 objects, like these cookies. What does 12 divided by 4 look like? Can you picture it in more than one way? You might have divided the cookies into 4 groups. In each group, there are 3 cookies, so 12 divided by 4 is 3. Here, dividing means sharing. Think of dividing by 4 as equal sharing between 4 people. Instead, you might have divided the cookies into groups of 4. 3 groups of 4 can be formed from 12 cookies. Here, dividing means measuring. Think of dividing by 4 as counting the number of 4 cookie servings. These two fundamental meanings of division, sharing and measuring, also apply to integers. Consider positive 6 divided by positive 3. Positive 6 can be represented using 6 yellow counters. Dividing as sharing leads to 3 groups of counters. In each group, there are 2 positive yellow counters. On a number line, dividing as sharing means 3 jumps in place of groups. Each jump is 2 units to the right. Dividing as measuring leads to groups of 3 yellow counters. There are 2 such groups in 6 yellow counters. On a number line, dividing as measuring means jumps of 3 to the right. 2 of these jumps land us at positive 6. Let's take a closer look at negative 6 divided by positive 3 and negative 6 divided by negative 3. How would you model each expression? Is it more helpful to think of dividing as sharing or measuring? Why? -6 can be represented using 6 red counters. On a number line, -6 is placed 6 units to the left of 0. We'll start with -6 divided by +3. Dividing by +3 can mean sharing between 3 groups, or 3 jumps. In each group, there are 2 red counters. Each jump is 2 spaces to the left. Therefore, -6 divided by +3 is -2. It is not helpful to think of dividing as measuring in this expression, because this approach asks how many groups of 3 yellow counters are there in 6 red counters. What about -6 divided by -3? It doesn't make sense to share between a negative number of groups. In this expression, think measuring. We can count the number of groups of 3 red counters, or the number of jumps of 3 spaces to the left. There are 2. 2 can be written as +2. So far, we've explored the following calculations. Something's missing. That something is +6 divided by -3. This time, neither thinking of -3 groups nor groups of -3 is helpful. It is helpful to think of the relationship between dividing and multiplying. If +6 divided by -3 is an integer, then -3 times that integer is +6. The integer we're looking for is -2. On to order of operations. Adam is a golfer. He records his score relative to par for each hole. What is his total score? You might have calculated a running total from left to right, or you might have grouped equal scores together. Repeated addition can be expressed as multiplication. First, we multiply each score from -2 to +2 by the number of times it appears on Adam's scorecard. Next, we add these products. Multiplication takes precedence over addition. This aligns with a collection of conventions called order of operations. I chose to add the integers from left to right, but there are more efficient strategies. Can you spot them? Notice that -4 and +4 are opposite integers. They add to 0. Also, +4 and +2 add to +6. The opposite of -6. Adam's total score is -4, or 4 under par. Let's apply our understanding of integers to solve the next set of problems. The temperature falls 2 degrees Celsius each hour. What is the total change in temperature after 5 hours? A decrease of 2 degrees Celsius can be represented by -2. This is repeated 5 times. +5 times -2 is -10. The temperature falls a total of 10 degrees Celsius in 5 hours. How many hours will it take for the temperature to fall a total of 16 degrees Celsius? -16 divided by -2 is +8. There are 8 -2's in -16. It will take 8 hours for the temperature to fall 16 degrees Celsius. Let's solve one last problem. Place 4 integers from -5 to +5 in the boxes below to make the greatest value. Each integer can be used only once. This problem brings several operations together, so we'll have to consider the order in which they are carried out. Order of operations tells us to first evaluate expressions in brackets. Next, we multiply or divide from left to right. Finally, add or subtract, again from left to right. We could pick and place integers randomly and see what values we get. Instead, we'll try a more strategic approach. We can begin by attempting to maximize the sum within the brackets. Placing the largest two integers, positive 5 and positive 4, in these boxes gives us the largest possible sum. Next, we multiply. We can place the largest remaining integer, positive 3, in the spot of the second factor. However, swapping positive 5 and positive 3 results in an even greater product. But there's a catch. Looking ahead, the next step will be to subtract. Subtracting a large positive integer will decrease the value of the expression. Subtracting a negative number, on the other hand, will increase the value of the expression. Let's back up and undo placing positive 3. Instead, make negative 5 the second factor. This results in the least or most negative product. Place positive 3 in the last empty box. Please know that this is a window into my thinking, which included a couple of missteps and revisions along the way. You or your child might arrive at this solution by taking a different path. What is the value of this expression? First, we look for brackets. Positive 5 plus positive 4 is positive 9. Second, we look for multiplication or division. Positive 9 times negative 5 is negative 45. Third, we look for addition or subtraction. Subtracting negative 45 is equivalent to adding its opposite, positive 45. 3 plus 45 is 48. Can you get this value in a different way? We encourage you to play with variations on this problem outside of this video. For example, what's the least value that you can make? Can you make 0? What if you use integers from negative 9 to positive 9? Let's talk about connections to BC's math curriculum. This video addresses several learning standards in the Math 7 curriculum. In content, we learned about operations with integers, specifically multiplication, division, and order of operations. Your child may be engaged in several curricular competencies in their classroom. Let's highlight a couple that were elicited in this video. We used reasoning and logic when we explored and made sense of the patterns we observed in products of integers. This involved representing integers pictorially by drawing counters and number lines. Finally, we connected multiplying and dividing whole numbers to multiplying and dividing integers. Engaging in these competencies and more through this content deepens your child's understanding of the following big idea. Computational fluency and flexibility with numbers extend from operations with whole numbers to operations with integers. In later grades, your child will continue to extend this to rational numbers, signed fractions and decimals, and algebraic expressions. We hope that you enjoyed this video and found it helpful when supporting your child in their mathematics learning. Please check out the other videos in this series.